Hello students, welcome back. We completed sections 1 and 2. Now let's go to section 3. This time we're going to study calculation problems. First, absolute extrema. Absolute maximum is the biggest function value and the absolute minimum is the smallest function value in a certain interval. And that interval is most of the time a closed interval. If it is closed interval, then yes, the problem is always well posed. But if you have an open interval or half open interval, then problem is not always definitely wrong, but there's good chance things can go wrong there. And here, closed interval, and this time entire real line, so there is some chance things may get wrong, but in this case it turns out to be okay because we are looking at periodic functions here, so essentially it's the same as a closed interval. Another closed interval, okay, all these problems are actually well posed. Now, absolute extrema, the easiest way is to plot. Look at the graph. X cubed plus x squared minus x, and then plot it from -1 to +1. Okay, kind of like this. And then, okay, what do you see? Looks like we have the biggest y-coordinate value here and there. Looks like that's y equals to 1. And the smallest right here, y equals to about -0.1 something, pretty close to 0.2. That's what I expect. Okay, alright, how do we actually find out? Number one, the endpoints are automatically candidates, -1 and +1. And then horizontal tangent. So we have to consider those three cases. So all right, f of -1, so that's -1 to the third power plus -1 to the second power minus -1, and that's -1 plus +1 plus another +1. Okay, that's 1. And yeah, y-coordinate looks like 1. How about +1? Okay, that's +1 to the third power, +1 to the second power, +1. So this is positive, another positive, and this one is negative. So in the end, 1 again. And look at this. Yes, okay, all right. So we have absolute maximum 1 at x equals to -1 and x equals to +1. So x equals to positive or -1. And then here's the reasoning. Okay, all right. Next, this one here, horizontal tangent. So we have to find out the derivative and then set the derivative equal to 0 to find out this x-coordinate value. So how do we do that? Take the derivative, 3x squared plus 2x minus 1, that's equal to 0. And then if you factor that, you're going to get the solution. Can I factor this? 3x minus 1, x plus 1. If I do that, I'm going to get, let's say, +3, -2. Yeah, that's a correct factorization. So we get x equal to -1, which is actually this point, and that too is actually horizontal tangent. If I extend this graph, x equals 1/3, okay, and that's what I'm looking for. And in that case, what do I get? F of 1/3 which is, oh boy, 1/3 to the third power plus 1/3 to the second power minus 1/3, and this I give up. I'll just put it into calculator. And then I get negative 5/27. This is correct answer, but I really don't know how large this is. So let's calculate the decimal value of it. And then negative 0.185 something. Okay, that pretty much fits. Pretty close to negative 0.2, but not quite. So what's the conclusion? Absolute minimum y equals to negative 5/27 at x is 1/3. So that's another conclusion that I can draw from here. So plotting the graph is usually a good idea. And then endpoints are automatically candidates. So plug in and do your computation. And then horizontal tangent. Take the derivative, set it equal to 0. And then do your computation. Among those, the biggest function value is the absolute maximum, and the smallest is the absolute minimum. So given time, you can do all these computations. And of course, you have graphical solution as well. Let's see, what do I have here? Take the 0, set it equal to 0. All right, I did horizontal tangent first. And then numerical computation, and the conclusion, and the graph. Oh, this graph is a little bit better. This is a portion I showed you before, but extend further. Oh, let's go back to this graph. If I have the entire graph, then this is a local minimum, not absolute, because far away from here, it can go down below. And this one is going to be a local maximum. This one is not a local maximum, but because its graph extends further here. Of course, if I restrict the domain, -1 to +1 only, then these are absolute maximum, and then here, absolute minimum. Absolute maximum and absolute minimum must always exist in any closed interval. And then the x-coordinates that attains the absolute maximum or absolute minimum can be multiple. In the example, we had only one x-coordinate value associated to absolute minimum, but we had two x-coordinate values associated to a single absolute maximum. But there's no chance you don't have any x-coordinate value associated to that. How about the next example here? Well, okay, let's have a plot. Okay, that's a plot. And then x equals to 1 here. All right. And then x equal to e here. And this coordinate axis does not begin from 0. Okay, we have this kind of graph, but it's not as good as the previous graph. Okay, all right, 0, 0 is right here, and at x equal to 1, let's see, greater than 1.5, less than 2, somewhere around here. At e, looks like I'm getting about 1.5-ish. So you have absolute minimum here and absolute maximum around here. That's what I see from the graph. Do you agree? Okay, all right. Without the graph, I have to calculate f of 1 and f of e. But with the graph, I don't have to bother with this one. Calculate f of e, then I'm going to get f of e is log of 8 e squared minus e to the fourth power, and what is this value? $1.5 something. And then that's the absolute minimum that's attained at E. Okay, how about the absolute maximum? Horizontal tangent here. So let's take the derivative and set it equal to 0. What's the derivative? Good question. We have a log function. So u prime over u, derivative of the new inside, 16x minus 4x to the third power. And then denominator is whatever that's inside, that just goes in. And then if I set it equal to 0, that means the numerator is 0. Negative 4x to the third power plus 16x is equal to 0. 4, factor 4 out, x, and then x squared minus 4 is equal to 0. And then x equal to 0, well, that's outside of the domain, so factoring this one further, I'm going to get 4x, x plus 2, and I'm going to get x equal to 0, invalid, that's outside of the domain. X equal to negative 2, again invalid, that's outside of the domain. X equal to 2, yeah, okay, that one goes right here. I get that. And that, in that case, f of 2, well, looks like I'll have to plug into calculator again. 8 times 2 squared, so 8 times 4, 32, and then 2 to the fourth power, that's 16. So that's log of 16. But then again, what is log of 16? $2.7 something. Anyway, that's the absolute maximum. So absolute minimum at x equal to E with the absolute minimum value 1.5 something. Absolute maximum at x equal to 2. Absolute maximum value is 2.77 something. Let's see, what do I have in my answer key? Take the derivative, set it equal to 0. I have positive or negative 2, but only positive 2 is valid solution in my domain. And then this one and that one, absolute maximum log of 16 at x equal to 2. And then absolute minimum, yeah, like that. Wait a minute, log of 16 is not 1.94 something. 2.77 something, yeah, I must have got it wrong. Look at the graph. Yes. Yeah, it's 2.77 something. 1.9 something has got to be this one. Sorry about the typo. I'll correct it. Anyway, that's how you do it. Take the derivative, set it equal to 0, get the critical point, and then punch the calculator. And then the endpoints are automatically candidates to punch the calculator. Biggest is the maximum, smallest is the minimum. And that's how you get absolute extrema. Not much thinking there, just a lot of computation. Yes, you have to take the derivative and set it equal to 0, but that's about it.